my presenting, I think I really need to have my video turned off.
Well, hello, everybody. This is Rick Hooper speaking. We'll just wait about a minute or so as people are continuing to sign on at the top of the hour. Um, then we'll get started probably about one past or two past the hour, so you know how people are coming on. And for those of you just joining us, we'll get started here in about a minute. Okay, well, it seems like it's slowing down, so let me try to get started then. So welcome everybody to this workshop on a software package called CyberWater. My name is Rick Hooper. I'm at Tufts University and past executive director at Quasi. And Tony Castronova from Quasi is also joining us. We really appreciate the time you're taking to join us today while we try to introduce you to this package. Uh, Neither Tony nor I are on the development team. We're basically here helping uh, Tzu Liang and Yao Lang, who are the two co-PIs on this project, um, on the community engagement aspect of this. And so we're at a stage now of the development where we are ready to sort of show you what we have, what the development team has done. We have had a kind of a user workshop last year. So the software package is reaching a degree of maturity that we're ready to sort of show this and get your feedback on it. So the development team is ready for your feedback, and we really want to know what's useful, what isn't so useful, how can you use the software. We have some ideas of how we think people are going to use the software, but it's always best to check whether our concepts are correct or not. What are the barriers, given the current state of development? What are the barriers to this use? And the bigger question really is that we need to assess as the CyberWater, as this development project ends up, and as we look at trying to see, do we keep this project going? Does CyberWater meet the needs of the community at large? Is it something that you're going to use? So in this webinar, and we'll have probably roughly 20 to 30 participants in this. So it's a large enough group that the easiest way to get your feedback will be by typing questions in the chat box. We do want to open up to allow you to speak at the end of every demo, and we really do need this feedback. That's why we're asking you here and taking your time. This is scheduled for roughly, I guess, 3 hours. And we hope that you can do it. We're going to try to keep it moving with fairly brief talks and brief demos that we can highlight important parts. So to give you a very high-level overview of what CyberWater is, it is a visual modeling environment designed for water-centric models. And it's using VizTrails as the modeling environment. And it basically just looks like this, where you're able to specify a time, space. Well, I'll get into this in a second. But the key aspect, which is why Quasi got involved at the early days and many iterations of this project ago, is that it uses web-based data services to access data from various agencies. And it has developed for models that take advantage of those web services. And so when Quasi got involved with the development of web services now, 10, 12 years ago, this was really the vision that we had, was that we'd be able to enable scientists to access data quickly and not spend all our time data wrangling. CyberWater is, I think, a great example of what the power of these web services can be. So all we do in setting up a simple model run, and Daniel will be describing this to you in the first demo, is you just specify a time period of interest, an area of interest. In this case, we just grab data, in this case from the USGS, and there's of the various visualizations and agents, one is just a simple plot, and you can plot the data. So this can be done on the fly. Grab data. And so this is, again, is kind of the concept we always had for where these data services and how these data services could be used. These key features will be described in the upcoming demos. It's an integrated workflow to show how we can specify the space-time, as I said before, get the forcing data required, convert the units as needed, as you see in that next batch of boxes, run the model, and then visualize the output. These data services provide access to data at continental and some at global scale, so it enables you to easily run models in different locations. It provides seamless access to high-performance computing, and that will be also one of the demos to show you how this works. In addition, this visual modeling environment has a somewhat different concept than maybe others that you've seen, that we enable you to bring your model into this, but with very limited adaptation. We'll say, ideally, no programming required. That might be a bit of a stretch right now. But the key concept here that's different from other environments, other visual modeling environments, is that the model is simply an integral unit. The objective here is not to come up with a library of process modules to allow you to mix and match, which of course is a much higher degree of software engineering required to make all that work together. And there are other projects that do that, like CSDMS. Here, the idea is just to enable you to run a model easily, quickly, allow others to run your model. And we see this as an important factor for example, using models in the classroom, of using this for teaching, but also if you want your graduate students to be able to run a model at a different location, that you can quickly change the location this way, and then you can ask other questions in terms of parameterization, et cetera. So these are the key use cases that we're considering considered while this was being developed. So really the question back to you is like, are these use cases correct? Is this how you can envision using this? And if not, please correct us where we're wrong. So the schedule for today, Sue Liang, so one of the PIs, will give an intro talk with an overview of the CyberWater environment. Then there's going to be a series of essentially 4 demos, each demo about 15 minutes long, first covering the CyberWater interface, then using GIS in CyberWater. We'll have a short break, and then a third demo on how you port your own model into CyberWater, and then a 4th demo on accessing HPC. At the end, there will be a survey. We really hope you take the time to fill the survey out. In addition, there will be brief poll questions at the end of every module, just to get some feedback. But of course, the Zoom polling capabilities are quite limited. And we'd like to be able to get a slightly more deeper feedback. And there will be a link provided at the end of the seminar for you to access basically just a Google form as a survey. And we really would appreciate if you would give us the 10 minutes or so it will take to fill that survey out. Okay, so with that, I will end there and pass the baton over to Tsu Liang at Pitt, who's one of the PIs on the
Sue. Thank you, Rick. Let me share my screen. Can you see my screen?
Yep, it's good.
Okay, sounds great. Let me hold on. Let me turn off my. I'm sorry. Let me turn off my video to save the bandwidth. Okay. Thank you, Rick. And welcome everyone to the CyberWater User Workshop. I'm Su Liang from University of Pittsburgh. I'd like to acknowledge the development team members of the CyberWater. They are listed here. In this slide, we have also the entire team members of the CyberWater project listed. I'd like to acknowledge their contributions to the project. So what is CyberWater? Well, CyberWater is an open and sustainable modeling framework software system. It enables an easy and incremental integration of diverse data sources and models. And it also enables reproducible computing and seamless and on-demand access to various high-performance computing platforms. So as the development team of the CyberWater, we aim at offering not only the capabilities of automatically have the data moves into the system from machine to machine access, the machine to machine access from the external data sources to diverse models, but also the capabilities of allowing the users to easily add your own models into the system. This is achieved through its open data and open modeling architecture, and which are realized through the data agents, model agents, or generic model agent tools and workflow. All of these are in one place. So the motivation of developing the CyberWater system is to try to address several challenges that we face today. For example, the challenge of accessing the heterogeneous data products. Oftentimes, these data products require different access protocols and APIs, and they come in diverse formats. Models are usually very complex nowadays, and they require significant data pre-processing. And coupling different models is difficult and challenging, and it is a time-consuming task. The other challenge is that many models now require high-performance computing capabilities. Another challenge is that the reproducible capabilities. Sometimes the simulations of the case studies are difficult to be reproduced, even for the same research teams, not to mention that it is also even more challenging to reproduce them for other teams. And so with all of that, oftentimes scientists and educators spend more time on the non-vital tasks rather than spend their time working on the core sciences. So with that, we want to develop this the CyberWater system. And here is an overview of this architecture of CyberWater. The brain of the system is its MSM core. MSM stands for Metal Scientific Modeling. And the various diverse data products are connected to the core through the data agents. and the various diverse models are connected to the core through the model agents. And CyberWater uses the workflow engine of Visuals and its user interface. So here is a preliminary view of how the CyberWater user interface look like. So this center part of it is the workspace. And these different boxes represent different modules. Each module accomplishes several tasks. And these modules are developed by the development team of CyberWater. And you can simply drag this module from the left panel here, where my mouse is, into the workspace and connect these modules to form your workflow and execute your workflow to accomplish what you want to accomplish. So the main functionalities of CyberWater we have developed so far include the following. The first, data agents, with which we can access various diverse data products from different data providers. And the next is the model agents, with which one can integrate the models into the CyberWater system. And the other way for the users to integrate their models into the system is to use generic model agent tools. And the difference is that with a model agent, the user needs to write a little bit of code and to handling the model interface. With the generic model agent tools, the user doesn't need to write any codes in order to integrate their models into the system. Both methods don't require the users to modify their source codes, nor to recompile their source codes. All you need to do is to use your executables. At present, CyberWater is able to handle executables from the C language, Fortran, Java, and Python. And we are working on handling MATLAB, which will be made available into the CyberWater when it is done. CyberWater also has this capability of making model couplings an easier task. It is integrated with GraphJS. And so the commands, all the commands that are available or included in the GraphJS, it can be used in CyberWater. CyberWater also offers on-demand access to various different platforms of high-performance computing. CyberWater also has a data fusion capability based on the multi-scale common smoother algorithm. With that, one can fuse different data products or different model results. CyberWater also offers graphical workflow environment. It offers visualization and animation tools, and also it offers the provenance based through the visuals. Okay, here are some examples where different data products are accessed through CyberWater data agents. Up till now, we have developed more than 10 data agents, which allows us to access various different data products from various different data agencies. For example, the radar data agent allows us to access the radar precipitation data provided by a National Weather Service, and it is shown up here. We can also access the data from North American Mesoscale Forecast System, and we can access the data from Global Forecast System, which is shown up here. We can access the soil moisture data from NASA's MAP, GPP and NPP, which stands for gross primary production, and net primary production data from NASA MODIS. And we can also access precipitation data provided by NASA GPM satellite mission. We can also access NLDAS and NCA LDAS data from NASA land data assimilation system. In addition to access those data, one can also access the USGS data based on our USGS data agent. With that, one can access more than 13,000 USGS stations. And this map shows the locations where those USGS stations are located. We can also access the geoscience data through the Unidata platform by using our Unidata data agent. One can also access sensor data from the Iowa flood information system using our data agent as illustrated here. So in terms of model agents, which are used to integrate the models, we have developed some model agents to help easy integration of the models and the illustration. For example, we have Vic model integrated into the CyberWater using two different approaches, both the model agent and the generic model agent tools, which I will show you examples later in the next few slides. And in terms of the Vic model, we have Vic model version 4 and Vic model version 5 integrated into the CyberWater. And by the way, for those of you who are not familiar with what Vic model is a net surface model and also a macro scale hydrologic model. We have the routing model integrated into the CyberWater through both ways, model agent and generic model agent tools, GT. And DHS-wave model integrated into the system. DHS-wave model is a high-resolution hydrologic model. And another model is CASA-CNP. This is a biological model. CASA stands for Carnegie Ames Stanford Approach Model, which deals with carbon, nitrogen, and phosphorus cyclings. And we are planning to also integrate the following three models into CyberWater. One is the Iowa IFIS model. The other one is the USDA Forest Service ecological model, which is called WASI. And the third one is a USGS environmental model, which is called FreeQC. Okay, here is an example of a workflow which execute Vic model in CyberWater using Vic model agent. So this is a Vic model agent, and the Forsen data required by Vic model are accessed and brought into this system through our data agent. And in this case, it's NCA LDAS data agent. And to run this Vic, you need to specify the time range, which is the time period of the model simulation, and the spatial range, which is the study area. And with that, you connect them and you execute this workflow, which will run the Vic model and generate results. And in this case, you can output the results, for example, the surface runoff and subsurface runoff from Vic and for visualization using our visualization module. And in this case, you can also compare the model result with the other product. In this case, we compare the surface runoff with the NCA LDAS surface runoff, and which is shown up here. This plot is obtained from this module. And this is a result of running Vic without calibrating any model parameters. And this is for this watershed, which is about 2,000 square kilometers large. Okay, this example shows how we can easily couple two different models in CyberWater. And this example shows the Vic model is coupled with a routing model here using model agents approach. And since the routing model requires DEM data and also the information from GIS, such as the boundary of the watershed and the flow network, flow path network, and so on. And so we have you get those information automatically from GraphGIS through our GIS engine. And remember that CyberWater is integrated with GraphGIS. And so through this, you can obtain all the information you need automatically and fit that information into your model, which is a routing model here, and execute it. And in this case, you build this workflow and execute it, and then you will be able to get the model simulate stream flow, and you can then compare it with the observations of the stream flow. In this case, it is the stream flow observed from the USGS. And so you brought in the USGS observations using our USGS data agent here. And then you compare them and display the comparison using this display functionality. And here is the results. And so the green shows the VIC coupled with the routing, and the blue is the USGS observations. Again, no model calibration was done. Okay, the next one, what I'm going to show you is to couple different models using the generic model agent tools that we have developed. So instead of using model agent to couple different models, you can use generic model agent tools to integrate your model into CyberWater and couple them. And here in the modules in the blue box here, these are the modules, you use these modules to construct your VIC model agent. And so these modules integratedly work together to serve as to serve the functionalities of the VIC model agent. So you basically construct this model agent using generic model agent tools. By the same token, you construct your routing model agent using our generic model agent tools, and these are the modules that you need to use to construct that. And then you couple them together to couple the VIC and the routing model. And the one thing I want to draw your attention to is that in this generic model agent tools, there is a module here called the run model agent. And if you use this run model agent here, which means that you execute your model, in this case, the VIC model and the routing model where my mouse is, locally on your local machine rather than remotely. And so after you build this workflow and then we want to execute that, again, in this case, we apply this workflow to study the West Branch Susquehanna River Basin, which is rather large. And again, we compare the results with USGS observations. And here is the results of executing that workflow. And as you can see, this watershed is rather large. It is more than 17,000 square kilometers. And again, the results are not calibrated. And this is an example where the DHSV model is integrated into the CyberWater system using the model agent approach. And this is a DHSV model agent. And you again use our data agent to bring in the Forsen data. And in this case, the Forsen data for DHSV model is different from the VIC. And so you use a different data agent. And again, you compare it with the USGS. And here is the result. Okay, and what I want to show you here is that CyberWater has this flexibility of integrating models through the model agent and the model agent tools. And also you can use them in combination to couple different models. In the previous examples, I showed you how to couple two different models using either model agents or both with model agent tools. And in this example, what I'm going to show you here is that you can couple the VIC model with CASA model, and using the combination of VIC as a model agent, here it is a VIC agent, and the model agent tools, here is that you construct the CASA model agent using the generic agent model agent tools. And you build this workflow and execute that, and then you display the carbon on the leaves from executing this workflow, and the result is shown up here. And this example is to show you that not only you can execute your model locally, for example, the Vic model, but also you can execute your model easily on the HPC, the high performance computing platform. And the difference is that you construct your model agent, in this case, the Vic, by using the generic model agent tools, and you see these modules here. The only difference is that you replace the run module agent by the HPC module agent here. So to refresh your mind, and if you want to run your model locally, you use this run module agent here. But if you want to, if you want to run your model remotely on the high performance computing platform, you use HPC here. Okay, what I want to show you here is that another capability that CyberWater has, it can fuse different data products easily using our MKS algorithm. And this is a schematic presentation of the concept and idea of what MKS is. And for those of you who are interested in details, you are welcome to read these papers. And what I'm going to show you here is an example where we use the MKS to fuse the 3 precipitation data products over this 1 degree by 1 degree region. And it covers part of the Susquehanna River Basin. And so the 3 data agent and the 3 precipitation data products we are going to fuse are the following. The first one is a radar precipitation data measured by National Weather Service. And we brought that data into the CyberWater using the radar data agent. And this radar data has its spatial resolution of about 4 kilometers by 4 kilometer resolution. And the second precipitation data product is the GPM satellite precipitation. And we use the GPM data agent to bring that data in, and it has a 0.1 degree resolution. And the third one is the NCAL dust precipitation data, and that has a 1/8 degree resolution. After you have these different data products brought into the CyberWater in real time, and then you can use our MKS data fusion module to fuse this data, and then use our visualization capability here to visualize the results. And here are the results. The first row shows the radar precipitation and data product, which is displayed at the 1/32 degree resolution. And second row here shows the GPM precipitation data from the satellite, and it is displayed at 1/8 degree. The third row here shows the precipitation data from the NCAL dust data product. And the last row here shows the fused precipitation data, and it is displayed at a 1/16 degree resolution. As you can see from this, sometimes by the way, each column represents the precipitation for the daily precipitation for that day. And we have 10 days here. So from this, what you can see is that they sometimes these 3 different data products give you similar magnitude of precipitation and also the spatial patterns. But sometimes the data gives you a very different magnitude in terms of precipitation intensity, and also the spatial patterns are very different. And so with our CyberWater tools, you can easily display the different data product. And also if you want to get fused data product, you can use our MKS capability to fuse them easily. And down below here shows the time series of the precipitation and from its data product and also the fused data. And each point here represents an area mean of this entire area. And so you can see the MKS time series is shown up here in red. Okay, with all that in summary, CyberWater has some unique characteristics. For example, its novel architecture enables a dramatic reduction in model integration complexity. So in CyberWater, the model integration complexity is linear as opposed to quadratic model complexity for those pairwise model integration system. And you know the linear complexity is the lowest complexity for a model integration system. And also CyberWater's effective model agent tools enables us to have an easier model integration and coupling with little to no coding. And CyberWater has the capabilities of incorporating diverse data sources and have them automatically flowed into your model in real or near real time. CyberWater's high performance computing facility enables its access to HPC on demand. And also it has the capability of supporting workflow and reproducible computing through the adoption of visuals. So the significance of CyberWater includes the following. For example, it offers an open and sustainable platform that can maximize the level of harmonization among diverse data sets for various model intercomparison, evaluation, integration, and coupling activities. It also facilitates the multi-model assessment using multiple data sets, and also it facilitates team collaborations. The CyberWater system is expected to be released to the community next year. Okay, so what do we like to achieve from this user workshop? Well, first, we want to brief you all, the community, the development of the CyberWater system. And that's what I just did. And next is to illustrate the features of the CyberWater through 4 demos, which will be presented to you by 2 PhD students, Daniel Noonan from Pitt and Zhen Chen from IUPUI. And we like to seek your comments and feedback on the features included in the CyberWater so that it will help us to increase its utility to education and research. At the end of the workshop, we'll conduct a survey, and we really appreciate all your comments, valuable comments, and your participation in the survey. Thank you very much. Are there any questions?
Thanks, Sue. So if there are any questions during the workshop, feel free to unmute yourself and ask the question. If you would rather not do that, you can type your question, any questions you have throughout the workshop in the chat, and I will take a look at that and bring those up to the speaker. We'll also have time for questions after, or in the next, after 15 minutes, we'll have time for more questions. So let's move on for right now. And Daniel Luna is going to take us through a live demo of the current CyberWater interface. So Sue, if you don't mind unsharing.
Yeah, let me stop sharing.
And Daniel, it's all yours. Thanks.
Thank you, Tony. So hi, everybody. Thank you very much for coming to this workshop. Again, I would like to encourage everybody to type all their questions and any comments you guys have in the chat so we can answer. CyberWater is it's intended for you guys, for the community to use. And we want you guys to let us know what you guys think and what can we do better. So let me share my screen. So let's start this set of demos with a demonstration of how we're going to build a case study in CyberWater. And for these case studies, we're going to use some data agents. So we want to show how the use of these data agents look like. And also we're going to use these data agents to connect them to the VIC model. As Dr. Lian explained before, this VIC model is a land surface model that we can execute it without any knowledge of the inner workings of the model in CyberWater. And
excuse me, Daniel, you can use the presentation mode.
Oh, sure. I think I have to jump off the presentation mode because I'm going to do the live demo. But then after this, we want to execute the VIC model for a big watershed. As you guys have get a sense of the capabilities of CyberWater in terms of scale. And we want to showcase some of the visualization capabilities of CyberWater. So let's just start right away with the first case study. And for this first case study, we want to use the USGS information, USGS data agents to bring information direct to your computer. So for any of the case studies, we have to start with defining the time window for the execution. And for this, we use this time range module that Dr. Liang showed before. And this time range requires an initial time and an end time as the parameters. We're going to run the simulation from 2010, January 1st. So the format is displayed in the label. Just going to go ahead and fill it in. And because we want 1 year simulation, you can just write 2011 at the end. And that's how you define the time window for your simulation. Then the second step is to define the area where you're going to run the simulation. And for that, we use the space range module. And right now, we're going to bring information for the French Creek watershed. French Creek watershed has an area of 153 square kilometers and is located in the east part of Pennsylvania. You can see it here in the bottom right corner. And the limits of this area have to be filled in here. Then the X max is the east limit of the simulation, the area. Then this one is going to be minus 75. This is the longitude, minus 75.56. Then the minimum is the west, minus 75.58. And then these two are 86. This is 86. And this is 58. And the Y max is the latitude, maximum latitude, which is the north. It's going to be 40.24. And this is the south is going to be 40.10. Just with this information, you're going to be able to define the time and the space of your simulation. And now we're ready to bring the USGS agent into the picture. As default, the USGS agent brings streamflow information. However, if the user wants to use a different type of data, you guys can change this in the variable code. And there's a list of variables in the USGS website. And the website is, everything is, you can find it in the documentation. So this button brings the user the documentation of CyberWater. We try to make sure to fill all the information that the user requires to be able to use the agent properly. And then the link for the rest of the parameters are listed here if the user wants to access them. And then we're just ready to bring a component to be able to plot the information in a time series, which is called the MSM show chart. What this does is makes an average of this area for the values of the data agents and displays them in a chart. We don't have to fill anything else. It's actually very straightforward. And this guy even tells us the units of the information that brings specifically is cubic feet per second. But if you want to change the units of the information that is brought up, the USGS allows us to do that directly with this unit conversion factor. But that's all we're going to show for the USGS agent. Now what we want to do is to be able to use this study case to be able to execute the Vic agent. So let's just start. You can just copy and paste the time range and space range pair. And we're going to bring the NCA LDAS agent. So the NCA LDAS agent is an agent that brings information from NASA, and the NCA data set, it has daily information of different variables such as precipitation, wind, temperature, minimum and maximum, and other hydrometeorological variables. So the way you use this is just by connecting the space range with the NCA LDAS. And how do you know the ports are compatible? You can check the name. So if you hover your mouse on top of the input port, you see this is called case study. And this case study is always a combination of time range and space range. All right. So you can choose which variable you want to download. Let's start with the precipitation, which is one of the variables that the Vic agent requires for its execution. And you can change the name of the box, kind of like to give it a pseudonym. We'll just call it precipitation. And this just allows the user to be able to see which components are already part of the workflow. And in order to protect the password of the information, the password of the account that the user requires to access this information, you can bring the password dialog. So the reason why you require a password to use this one is the NASA protocol, which is the OpenDAP protocol, the one that is used to bring NCL's information, requires the user to have an NASA Earth account. And this NASA Earth account is required by CyberWater through this password and username. So you can just fill out the username here, and then the password can be accessed during the execution time. So you can protect the information of the password for the user. Okay, so we need more information to be able to execute Vic agent. We need the information of precipitation, and then the wind, and we need the information of temperature minimums and maximum. So we can just bring them here. I already have this prepared. This is the same NCL as agent. Just this one has the speed, wind speed, and this one has the temperature maximum and the temperature minimum. The only thing we need to know is just connect this case study that we have previously prepared. And we have to connect the password as well. So you have to make the port visible. And by that, we have to click on the icon on the left. So CyberWater also shows that port for the user. And what these guys do, these are downloading a set of maps between the times that we have selected and covering all the space. And just as a demonstration, we can see, I prepare a small example of, we're downloading temperature for the entire US. And while during the execution time, it's asking me for the password and the username. And then what you're downloading really is a single map for every single one of the time steps. And one way of visualizing this is with the animation component in CyberWater. So this is just one example where we're downloading the entire US, but in this case, we're just using a smaller sample, which is the French Creek that only has these limits. Okay, after this, we would have to pre-process this information because Vic requires the forcing data in different units. For example, it requires, this brings precipitation, this brings temperature in Kelvin, when Vic, in this case, as default, Vic requires the temperature in Celsius. So we need to transform this Kelvin to Celsius. And for this, we have a very convenient component called the MSM unit conversion. We just go ahead and add it to our workflow, and we connect this to the MSM unit conversion. And what it requires is the new units going to be Celsius, and the operation, how you use this is you put X, and X is going to be our previous data set. And any mathematical operation that you write here is going to be applied to the entire set of maps that is brought by this NCAL agent. So to transform between Kelvin to Celsius, just have to subtract 273. I'm gonna do the same. You can just name this Kelvin to Celsius. I'm gonna use the same one to transform the minimum temperature. And I have prepared one for the precipitation as well, because we're gonna execute Vic in a daily basis. So because the precipitation comes in millimeters per second as a default, we need to change this to millimeters per day in the units. And with all this, we're ready to bring the Vic agent. Vic agent is actually very simple to use. We only need to add the required forcings for this in the appropriate units. And if you guys don't know where the units are or are unsure which units are necessary, you can just go ahead to the documentation and see which units are required for each one of the variables. But for now, you can hover here and see which ones you should connect to which ones. So here is precipitation. So we can just go ahead and connect the precipitation. The second one is the wind speed. And we connect the wind speed, and we need to make available the temperature maximum and the minimum, because they're not always required for all the simulations. So first is going to be the minimum, and then we're going to connect the maximum, and that's all we need. And then at the end, if we want to see the results of the simulation of the Vic agent, we can just bring our show chart module, and this one would automatically plot. It would compute the average of every one of the maps in that area and plot them as a time series. So the first one is going to be the surface runoff, and this one is going to be the base flow. And just with this, we can execute this workflow and password. And this is the result of the simulation. So there's one task that we are not really doing in real time, which is downloading the information. We have previously downloaded the information. We have the maps in our computer, and this happens for all the users. We have the maps on the computer. On the user is free to delete those maps, and next time you execute any of the data agents, so those maps are going to be deleted. But what the advantage of this is that we don't have to make the downloading process, which is the process that takes the longest time. But this is true for any type of download task that you have to do. This is not a limitation of CyberWater, but more a limitation of the servers that provide the data. Okay, and then after this, so this is the end of this part of the demo. Then after we're done with this, I would like to show the a very pre-made workflow that executes this West Branch Susquehanna Basin, which is much larger than the previous French Creek Basin that we showed before. It has 17,000 square kilometers. It is entirely located inside Pennsylvania. And the other difference of this execution is that is executed in an hourly basis. And for this, we use the NLDAS agent, which is different from the previous NCLDAS agent. And this one brings hourly information. And there's other few things in this setup. The first thing is we're plotting. Well, here I select to plot the DM information. The second, we have coupled the Vic agent with the routing agent, so we can calculate the stream flow of this simulation, and we can compare it with the USGS measurements. And the third thing is I connected an animation just to showcase how can we check, for example, the data in the middle of the workflow, just to make sure that the data we are feeding to our models is properly, it like looks well. And this is the animation of our, so this is the wind speed. Actually, the calculation of the wind speed, because we have the two vectors, the vertical and horizontal speed of the wind. And this is the hourly information of the wind speed in that West Branch Susquehanna area. This is the map, the DM map. And what we do here is we have to resample this spatially because the original map has more than 1 million points, and displaying this in my graphics card, it would take a little bit longer, just a couple of minutes longer, because we want to do this like in a quick fashion. I have to resample this map, and then the results. These are the result. The comparison. The green line is the results of the coupling between the Vic agent and the routing agent, and the blue line are the measurements of the USGS agent. And with this, I finalized the first demo that we have prepared for you guys. If there's any questions, please let us know. And feel free to unmute yourselves.
Yep. Thanks, Daniel. Before two questions have come in. Before I read those off, we have a poll, and we're gonna pop that up on your screen real quick. So just let's take 2 minutes and just look through this poll, and then we'll get to some questions and some discussion. Okay.
Okay.
Oop, what's going on here? Let's try it again. Launch. Is this poll appearing for anybody?
Seems not.
No, is that because Daniel has to stop sharing?
Do I
Yeah,
have to
let's
stop?
try stop sharing
Okay.
for a second, and let's see if that works this time.
Supposed to be in the chat or elsewhere?
That is interesting. Okay. Perhaps. Well, how about we? I will debug this a little bit, and let's get on to a couple of the questions. So the first question, Daniel, is does CyberWater allow users to configure their model simulations using a file instead of the graphic user interface? Because this may be convenient for experienced users setting up large simulations.
So the answer to that is yes. We have this suite of generic tools, and using the generic tools, a more experienced user can use a model in a more flexible way. However, this way of using the model agents allows the user to modify some parameter files. So if there's parameter files that don't change, of variables that don't change with time, those can be modified in the computer, in the local computer, and the next time you execute the model, then this model agent would use those files instead of the original ones to use the execution. But the configuration file, to modify the configuration file, I'll suggest to use the generic tools, which we're gonna demonstrate in the third demo today.
Okay, thank you. And the second question we have is regarding the data sources. The question is, does this only work for USGS data sources, or can we use other in situ measured data?
Absolutely. We have a module called directory to dataset, and we're planning to add an extra module that uploads time series directly, because you can also upload a time series with the directory to dataset, but the formatting is a little different, more complex. We can definitely make this just to upload the time series directly into CyberWater. But right now, you can absolutely use your own data to upload it to CyberWater.
Great. And another question just came in. How is CyberWater dealing with discrepancies between spatial and temporal resolution of data sources? So, for instance, rainfall and DEM resolutions that don't match.
Yeah, correct. That's a great question, actually.
Oh, actually, then there's a follow-up. If you can also talk about if it deals with irregular meshes.
Yeah, so when the resolution, irregular meshes. So when the grid isn't consistent. Okay, well, let's first start with the different spatial and temporal resolutions. We have two modules to deal with this. So the first one is the module I already showed. Actually, I don't know if I should share the screen, or you need the screen.
Go ahead
You can just mention it.
So, okay, so the first one is this resample. You can change the resolution of your data set in order to match it with other data sets, because definitely for some models like the VIC, you definitely need all the forcing variables to be in the same grid. And we have the time resample, time rescale, the time rescale module, and this one allows you to change the either aggregate or disaggregate the time resolution of the time granularity of your data set for them to all have the same resolution. So you can use this to tackle that problem. And the regular grids, we are not yet able to deal with them, but in order to run the Iowa model, if I'm not wrong, Dr. Liang can correct me with this, but to run the Iowa model, we'd have to tackle irregular grids. Technically, because we run the Vic agent, as long as the cells don't interact with each other, they could have any shape they want. That's the only limitation we have right now. If Dr. Liang wants to add something regarding that.
Yes, that's correct, Daniel and Ricardo. Yes, right now we have only tested for regular grids, and we are going to tackle that irregular grids and say what kind of extensions do we need to make from the development perspective to tackle that. And that's definitely on our to-do list, and we'll use Iowa model, which does the irregular grids as an example to illustrate that when we're done with that. Thanks.
Thank you. Thank you for your questions. If there's any other question, please feel free. You can also unmute yourselves and make the question directly.
Yep. While we wait, let's try this poll one more time and see if anything has changed. All right, it looks like you guys.
Yeah, I can see now.
All right.
Yes, this time works.
Fantastic. Okay, we'll just wait about one more minute. Okay, so that's, I think everybody has responded that's going to, so thank you all for participating in the poll. We have a couple more questions, Daniel, that have come in. And the first one is, the first one states, I was wondering if the nodes can be exported, created and modified in an editor environment. I'm not sure if you need more information on that question.
Yeah, I would like to know, what do you mean with nodes specifically?
So Tahir, feel free to unmute yourself and maybe provide a little more context.
Yes, sir. Hi, this is Tahir. I was wondering if the nodes, I mean, you have a node structure where you connect, the connection between different nodes, between different agents. So that's what I meant, that, for example, like GraphViz has this kind of capability to generate these kind of nodes in a pragmatic way. So I was wondering if that's something that can be done with CyberWater.
So you mean with node, you mean every one of the execution node, or like a cell for the accumulation?
The generation of the nodes themselves, not just the execution of them. Just when you want to generate the nodes, to connect the dots with connects the nodes, with mouse. So I was wondering if you can achieve that with, writing a code that kind of makes these nodes a structure.
Daniel, I think the question here, the nodes indicate to your workflow items. So each module. So basically one node maybe is one module.
Okay, so each one of them
Like for
modules
example,
is
you have
everywhere. Yeah.
US.
So these boxes, wait,
Mhm.
let me share the screen again. Yeah, so like each one of these boxes.
Right. Yes.
Okay. Yes, that's actually a good question. So we have this Python source. So this is a kind of like a dynamic module. You can modify this actually without leaving the user interface. In this edit configuration, you can add input ports and output ports. So if you need to do any kind of middle ground modification, or like a modification in the middle of the workflow or at the end of the workflow, you can do that here. But for this, you do need to make the code, definitely. And the code it requires is Python. And to modify this, so we're trying to do whatever possible to reduce the amount of coding that the users require in order to run this. But the idea of these agents is that the users are encouraged to create their own agents for sure. And we have reduced the amount of tasks or the steps required to add more agents into CyberWater.
Great. So we have one final question from Ricardo, maybe before we move on to the next demo, Daniel. And it's how is the coupling between the land surface models and the routing models being done with respect to the spatial discrepancies and resolutions?
So right now, this routing agent is actually running with the same resolution as the big agent. The only detail is that the drainage network, for example, is done with the DEM resolution. So those are the differences. So by default, this routing agent uses the DEM resolution to create the drainage network, but the uses the resolution of the big agent to get the flows, either the surface runoff and the base flow to do this. But because this routing agent gives just a single point, which is the output of the watershed, then this one actually does not have spatial resolution in the output, but does share the time resolution of the input. I hope that answers the question.
So, I think it's time to move on, but I made one more comment that just came in that I think you should consider. It's regarding how I believe how the different agents are being displayed, and that using something like a directed graph, looking at graph viz as an example, might be helpful to convey maybe the flow of data.
So yeah, that graph viz, I'm not familiar with it, but it's an awesome advice, and thank you very much for the suggestion. I might take a look at it. Thank you.
Okay. So I think that's to stay on track, Daniel, if you don't mind moving on to the next demonstration.
Someone is asking if there's going to be a link to the webinar in the future. I understand that yes.
To the recording of this webinar,
yeah,
we can provide that. Yes.
Okay. All right. So moving forward in our second demonstration, now we want to showcase the GIS capabilities of CyberWater through our GIS engine module, which is the one in charge of connecting the CyberWater to the GIS engine. And then we're gonna demonstrate how to use this GIS engine to run any of the commands available. In this case, we're using GrassGIS, and then how we visualize those results inside CyberWater. So we're gonna do make a GrassGIS performance task and then see the results directly in CyberWater. Oops, and then we're gonna demonstrate how this GIS engine is used to run specific modules like models like DHSVM model, and we're gonna compare those results of DHSVM with the USGS measurements. So let's let's just start with it. You know, let me close this because those take some memory. And then oops, sorry. Let me begin with a new one. Okay. So I have previously prepared partially this workflow partially, but let's just start with the GIS engine specifically. The GIS engine is part of the agent tools, and as by default, it has the path to the GrassGIS that is installed in your computer. But if you install it, if you happen to install it in a different place, you can change that here in the GrassPath file. So you don't have any issues, because we had those issues before. When users have GrassGIS already installed in their computers, we don't want the users to run into these issues anymore. And this GIS run module agent is the generic module to execute any of the GIS related functionalities inside CyberWater. So the first thing we need to do is just connect the GIS engine, which is the one that is going to tell this GIS run module agent how to connect to the GrassGIS. And then it's very simple to use. We only need to give the name of the command that we want to run in GrassGIS. So as long as you know the name of the command, you can use this. And then giving the parameters of that command directly to GrassGIS, separated by a semicolon. So right now we're going to import a text file into CyberWater, into GrassGIS from CyberWater. And that command is called r in text. Just going to import a raster map. And then how to use the parameters, or how to fill this input. You have to give these parameters in order, and the instructions for this are inside the GrassGIS documentation, in the CyberWater documentation. And the parameters that this import text raster requires are the output, the path, and then the coordinates. So let's just call it, this is the name of the output map that is going to be created in GrassGIS. Just call it temp elevation, and then the semicolon, and just let's go and fill up everything else here. So this is the path where this file exists in your local files. These are the limits again. So we're running a much smaller watershed called the Indiantown Run Basin, and these two are just flags for GrassGIS, which is if we want to override a map that already exists inside with this name, if you don't add this and it happens to have another map, then it's going to fail. And then quiet is just not to get so much text in your console. And just with this information, you can execute this function. And then the only other thing we need is just a flag to start. This is the only way to control commands that are going to happen in a sequence back in GrassGIS. So you just have to say, this is true. This guy is ready to start. Okay. And then the second one, we're just going to keep adding this GIS run module agent and connecting to the GrassGIS. And then this one is going to be G region. Wait, the common name is G region. And then the parameters is going to be the name of the elevation map. And then what this guy does is just to zoom in the working area of GrassGIS directly into the elevation map. And what we do now is, if we want this module to be executed after the first one, we just need to connect this one into this one, which is, this one gives the flag that is ready. This one receives the flag that is ready. So this one is executed after this one. All right, so just name this so we know what's going on, or in text. And then this one is going to be the G region. Then the next one is going to be the one that creates the watershed related maps. And the command is r watershed. And I have the inputs here. Then what it does is it takes an elevation map and creates the drainage map, which is where each one of the cells are going to drain, streams map, the accumulation map, and then these are the threshold is the amount of cells that are going to be accumulated before we consider this to be a river, then the amount of memory we're going to use in our computer in megabytes, then the same flags we had before. So I have this previously prepared here. I'm just going to go ahead and see the names. Temp elevation is the name of our elevation map. These are going to be the names of the other maps we create. 300 cells is going to be a river, and 1,000 megabytes for the memory. And then we just want to get all this information, and the parameters right there. Okay, so we connect this in ready to start, and we can connect this GIS engine. Okay, and the last part is the outputs. So the outputs are just a way to output this information in a text file so CyberWater can read them. Because right now, up to this point, the maps exists only in GrassGIS. We need to take them out from GrassGIS and be able to upload them in CyberWater. And for that, we have this our out text. Just go ahead and connect this into our workflow. And okay, and now we have to add a module to be able to upload that map that exists somewhere else in our computer directly into CyberWater, which is one of the questions we addressed in the previous set of questions. It's just called directory to static dataset. And this directory to static dataset requires the variable name. The variable name is going to be elevation because that's the map we're going to export here. It's actually here. And then the directory name is going to be here. Now the user is also encouraged to use this button, so you can actually go directly into your own directory path and open the file. Let me just double check we have the right, yes, inside DEM. Yep. So let's just go inside DEM. Okay, then the units are going to be meters, and then that's it. And if it's ready or not, then we're just going to make this visible and just tell this guy that we're ready. And the only other port that we need is a space range. So we do need a space range box that has the coordinates limits of the same area that we have described in this R in text. So that's here, and we connect this space range directly into a directory to static dataset. And the only thing left is this MSM show dataset. So this is a different way of displaying. This one displays one snapshot of the map at a time. So if you have a dataset that has multiple maps across a time series and a time series, and it's going to display one snapshot at a time in kind of like a spreadsheet. We can just go ahead and just try to execute this and see if we have any issues. Okay, this index are arranged. Let me just double check we have this set up. Okay, I missed the name of the command. Okay, so we're able to successfully import our DEM map into CyberWater, and this is the DEM map that is being created in GrassGIS. So now what we're going to do is, I'm just curious of the other maps that we have created in Grass during the execution of this R watershed. So for that, we have this, well, the first one is to use this information of these maps to delineate the watershed that is in this area. And for that, we have this R watershed outlet command that exists in GrassGIS. Then we can just connect this to the GrassGIS engine and then just give the flag that we're ready. We have to execute this after the R watershed because this requires some of the maps that are created in this step. And then right after this, we are ready to plot all the maps that we have created so far. So the only thing we need to do is just to give them the ready sign to every one of this. So this one is ready to start because this one is the drainage map. This one is the streams map. This one is the accumulation. Yeah, one is ready too. And then, okay, and this is the watershed map, which is generated after this one. That's why we have to connect this after this one. And then everything else has to be connected to the GrassGIS engine. And just gonna go ahead and connect this to the GrassGIS engine. And just with this, you can just use this. You see how you use this GIS raw module agent to execute any of the GrassGIS commands available. And we're just gonna give the space range because all these maps exist in the same space range. I think we're ready. So okay, so the maps are being plotted in the spreadsheet of visuals, and this is each one of the maps we have created using the grass commands. So the DM map, this is the drainage direction map, this is the accumulation map, this is the watershed map, and this is the streams that are in that DM map. Okay, and we can move on to the next step, which is using this GIS engine to execute a model like the DHSBM model. So I have previously prepared this workflow where we're using this GIS engine for two of the modules. The first one is this MSM compute excite output, and there's the DHSBM agent. The reason why we need this GIS to compute excite output is because one of the major things or the major source of errors or major source of kind of difficulty for the users is to be able to know exactly where the coordinate of the output exists in a model that applies either for the routing agent or the DHSBM agent. And for that, we have created this MSM compute excite output, but it requires the GrassGIS commands for that. So that's why we need to connect them to this GIS engine. And what we're doing here is we're running a 1 year from 2007 to 2008 simulation. It is done in an hourly basis. That's why we use this an LDAS agent, and we execute the DHSBM agent. And because the DHSBM gives information in the same time resolution as the forcings, then we have an hourly, we have cubic meters per hour. We need to transform that into cubic meters per second if we want to compare it to the USGS results. And these are the results without any type of calibration. These are the results without any modification of the parameters from the DHSBM agent. And I think with this, we're done with the demonstration, the second demonstration. If there's any questions, you guys can type it on the chat or go ahead and mute yourselves, and we are happy to answer any questions you guys have. Thank you.
Thanks, Daniel. As you guys are, one question has already come in, but as you guys are typing questions, I am going to start another poll, a very, very short one. Just take a quick second and complete this. Thanks. Okay, a few more seconds if you haven't had a chance to do that. Okay. Thanks to everyone who completed that poll. So the first question, Daniel, is regarding kind of a workflow dialogue or a wizard to help create some of these GIS pipelines. So is it possible to have a workflow dialogue to guide more inexperienced GRASS users through the GIS process? It could be something like a software installer, I'm guessing like a wizard, that would walk the person through dialogue steps, and then CyberWater would create the flow chart or the workflow chart that was kind of shown in the demo. Is that something that is possible?
That is possible. That is possible, and we can look into this. However, for now, we encourage the users to go just directly to the GrassGIS documentation. They have a very nice set of documentation for the users to be able to kind of learn how to use each one of the commands. It's very complete and it has everything the users need to know. So, but we can definitely create a little manual for the basics, which is, for me personally, the only like major thing you need to know before you execute anything in Grass is just being aware of this region. Everything else is pretty straightforward. But thank you very much for the question.
So
Okay, go ahead, Zoom.
yeah, so basically one thing I want to mention is that you don't really need to know all the things about running Grass.js, as long as you check the manual of Grass.js to know what are the commands that are available and their syntax, and then you are ready to use them. And CyberWater allows you to use them in CyberWater, so that will be very easy. You don't need to deal with all these other hurdles that you may encounter by running the Grass.js software.
Thanks. I guess we'll wait in case there's any other questions that come in. Wait a couple minutes here. And while we wait, I will give a quick update as to what's coming up with the rest of the workshop. So when we're done talking here, we are going to take a break and reconvene at 2:45. So this is, if you're, a good time, if it's lunchtime, maybe grab some food or a drink. And then we are going to reconvene at 2:45 and talk about porting models to CyberWater. So adding your own models using the generic model agent. And then we're also going to be talking about using high performance computing resources. So, okay, so there's one more question has come through. It's, the pipeline gets complex very quickly when you're doing this GIS things. Is there a way to just automatically rearrange all of the boxes? Daniel, are you muted?
Sorry. Thank you. It's actually, I was saying this is actually a pretty good question. And the reason why we display this in an ungrouped way is just for the users to get a sense of how the workflows look and what components it has inside. But you can definitely group the sets of components inside CyberWater. So you can just select the components you want to group, and you can go to edit and in workflow and group them in a single thing. So you can name this, for example, four things for Vic. So you have an idea what is inside. And if you want to undo that, then you can just, again, go to workflow and ungroup, and you get the components back to the place where they were before. But thank you very much for the question. Very important.
Daniel, I noticed when you went to that menu, there was also an option for re-layout. Does that automatically put them in different layouts?
Yes, it actually does. I don't like it, but let's just do it. You see?
Okay, so it doesn't do it in always the most convenient way.
Relayout. There you go. Yeah, this is the relayout of
okay,
these fields.
And I have a question.
Yes.
When you group together resources, that's a convenient way of cleaning up the workflow a little bit. If you wanted to make changes and change the way things are connected, do you have to ungroup them, make the changes, then regroup, or can you edit them when they're grouped together?
So far the only way I found to do this is by ungrouping them. You have to ungroup them. Yep.
Okay.
Thank you.
So it looks like we're coming right up on 2:30, which is when this portion of the demo or the workshop is supposed to end. So why don't we stop 3 minutes early? I'm going to pause the recording. Feel free to stay in the room, and we will reconvene in 15 minutes. Yeah, at 2:45, and we will talk about porting existing models into CyberWater. Okay, so everybody, let's take a quick break and stretch our legs, get a coffee, get some food. Thanks,
Tony. Yes,
Thank you, Tony.
Let's take a quick break. Thanks, everyone.
2:55 p.m. is Easter time.
Yes,
Just let everybody knows.
that's true.
Oh yes, that's very true. 15 minutes from now.
Yeah, 15 minutes from now. Thanks, guys.
Okay, I hope everybody had a nice 15-minute break. Hopefully a few people that dropped off will be rejoining us. But Daniel, whenever you're ready, I think we can get started again.
Thank you, Tony. The next demo is actually very short. We can wait a
Oh.
little bit.
Okay.
Yeah. I think we can start recording again. There you go. Thank you, Tony. So welcome back to the CyberWater workshop. So we're going to move forward to the third video, the third demonstration here, which is related to the uses of the generic model agent tools. So I just want to demonstrate how to use them. And for this, we're going to run the same simulation that we executed during our first demonstration. And I'm going to just showcase two different scenarios when the user uses initial values and when the user doesn't use the initial state files. So let's just start with, I have previously prepared the same case study that we have executed for the first demo, which is in the French Creek, which is a small watershed in the west part of Pennsylvania. And I had our 4 data agents that, just as a reminder, they bring daily information from NASA. And we do the pre-processing of that information by transforming the units into the proper units we need. So in our previous example, we just brought the model, which in this case was the VIC agent. In this case, we want to bring the generic tools. So the first component of the generic tools is called the main generator. And the main generator is going to act as the gatekeeper of the generic tools. So it's going to receive the same information that the model would have received if it was here in its place. So the first thing is the first parameter is the path, which is the folder, the local folder where the simulation is going to be executed. The user can just click here in the file icon. It will just take you straight to the file, the browser, file browser of the
Daniel,
computer.
Daniel,
Is your
you
screen
need to share your.
Oh, sorry. I thought I was sharing the screen. I'm sorry.
It
Thank
sounded
you.
like you were giving an overview for a little while.
Yeah.
Thank you. Let me see. There you go. Okay.
Oh, yeah. Could you just repeat what you said?
Sure. I actually can redo it. It's actually very, very short. So what I did is I brought the this is the case study, which has the time range and the space range of the first demo we had, and these are the 4 data agents. And we have, as you can tell, the same layout we had for the first demo. And we can bring the main generator of the generic model agents. And again, this is the first component is the path where the execution is going to be performed. We just go ahead there and just go straight to the path where we're going to have the execution, which is this main agent is going to be the folder we're going to execute the model agent. Oops. There you go. Okay, and this one is going to be the global parameter file or the configuration file of the model. Not all models have global parameter files, but because we're running VIC this time, we do need a global file. So we need to go to I have prepared a folder here with all the source files. So just gonna go and pick our global file for VIC, and that's gonna be added. And then the third thing is we do need to be consistent with the input we had. The input we had in our global parameter file, because the global parameter file for VIC sets an order of the forcing files. So how the forcing files are going to be received. The same order that is in that VIC folder file has to be respected in this main generator. So in this main generator, the first variable we had is the maximum temperature. So that's the first one we have to connect here in this data set 01, which are the forcings. Then we have to make the second one available for the minimum temperature. And then we have precipitation and then wind. So we connect precipitation first and then the wind. So as long as we respect that order, we're good to go. Then the second component is the component that takes care of the parameters of the simulation. This case is called the area-wise parameter generator. Just added here. And it has these ports where the user can add as many parameter files as they're required. In this case, we have 5 parameter files pre-organized in this source folder. Thing is, yeah, just making sure it's the same. Gonna collect the cell fractions. These are all parameter files that are required by VIC. So there's 5 in total, the soil parameter file, the vegetation library, and the vegetation parameter file. All right, and then we have to pick, this is the name of the folder that is going to contain the parameter file. So in this case, we're gonna call this parameters, yep. And this one has is going to receive the path of the generic tools in the main generator. So this main generator has this GT path. Just connect this one here, and so the parameter agent is completed. And we need another parameter, another agent for the forcing files. Just called forcing data file generator. And this one, you can set up the name of the forcing files, for example, if that is something fixed in your model. But for VIC, the name of the forcing folder is set up in the global file, and in the global file, and this global file is set as forcings, which is the same default that this forcing data file generator has. So we don't have to add anything. We just connect this dataset class to this one, because this one needs to get all the forcing information into the format that VIC requires, and this is the same format that DHSBM can run and CASA CNP can run as well. And also our routing agent is capable of doing that as well. And then this one is the same GT path that we had before. And with this, we're ready now to add our last section of the generic tools, which is called the run module agent. Run module agent, this one. So this one has 2 main objectives. The first one is to actually execute the model we want to execute with the executable file. That could be in all the formats that Dr. Liang explained. And the second responsibility is we have to tell him how to read the output files that are going to be generated in the execution. So what he needs is, this is a set of ready flags. They're going to be just going to let this guy be executed in order. So you're just going to feed this with the previous generic tools. And the other 2 are familiar GT path and dataset class, which are the same that the main generator gives. And then the other parameters are how to read the data. So this is the position of the column that we're going to read in the files. So the first, because we want 2 results, the surface runoff and the base flow, then the surface runoff is in the 5th column. As a user, as an experienced user, I have to know which columns are contain which information of our model. And then this is just to give the name. This doesn't have any real impact in the execution. This one is just for the labels. Surface runoff, just for us to know what we're plotting. And this one is going to be the base flow. There's other rules. For example, if it's going to be a point output, meaning if the result of our model is a single file or if it is distributed in many files. In this case, the results are distributed in many files. So what we have to give is the name of the prefix of all those files, which in the case of Vic is fluxes. But this can change to be a point output in the case of DHSBM, for example. Also, if the user has other parameters like number of header lines that we want to ignore, or if the file separator is not a tab or a space and is something else, then you can modify that. Okay, in the argument, this is the argument of the executable file. And in this case, it's just the name of the global file. And this executable, this is not a specific file because not all executables are executed in the same fashion. So if you have a Java, for example, executable, you need to add the Java parameter beforehand. So in order to give more flexibility, we have left the generic tools flexible enough for the user just to change this however they want. This is the location of the executable file in my machine. And this is really all we need to execute the Vic using the generic tools. The only thing we're missing is a way to visualize the data. So for that, we bring our old friend MSM show chart. And this one is going to be our base flow. This one is going to be the surface runoff. Surface runoff. And then, okay, and then we connect the first output, which has to be consistent with this. The number, this is column 5, surface runoff. And the second one is going to be column 6, base flow. That's it. Let's see how we do. Okay. There we go. Okay. Okay. Because the raw module agent doesn't know about the units, there's one last step I missed, which is giving actually the units. And we can give the units in this MSM show chart. So you can set up the units here. The units of this model are going to be millimeters per day. So millimeters per day here and millimeters per day here. And now when we execute this, you're going to see that we have the units already in the axis of our graphs. Let's just delete the other two. Okay, and the next example is, okay, what if we have an initial state file for our model agent? So there's the last component of our generic tools. It's called initial state file generator. And this one acts in a very similar fashion as the area-wise parameter generator or the forcing data file generator. It just requires the GT path that the other two required. It gives away the ready flag the same fashion as the other two. And the only thing I need to give is the path of the state file. So because in this case, we need a state file, then I have to give the location of the state file, which is called state 0101 2010. And that's it. There's another change because the initial state file changes the shape of the global parameter file, that we need to use a global parameter file that has that specific initial state file indicated. And just with those two changes, we can make a different type of execution. I would like to compare these results with the previous results we had before. This is the ones on top are without having initial state file. And the ones on the bottom are having initial state file. And with this is the end of the third demonstration I have today. If there's any questions, I encourage you guys to unmute yourselves and go ahead and ask, or you can also type the question in the chat if there's any. Thank you.
Okay, before, while we are waiting for questions from the audience, I want to make a couple of points here. One is that Daniel showed you the flexibility of using the generic model agent tools to construct your own model agent to integrate your model. So before the break, Daniel shows you how to integrate a model into CyberWater using model agent. And here he is showing you how to integrate your model using the generic model agent tools. And so that's one thing and to keep in mind. And the second thing is that when you the second thing is the initial state file versus without initial state file. And so for example, for some models, the initial states, let's say the soil moisture initial states, are the default values in their source code. That is fine. And if that's the case, you don't need to have initial state files. So which is like Daniel showed in the first demo. The second one is that some models do have initial state files, and then you use that module from the generic model agent tools to construct your model agent. That is what he did in the second example, where the results are shown in the two bottom plots. And so the other thing is that even if your models don't require initial state variable files, states files, you can still use this initial state file generator module. The reason is that because if you want to do data simulation, for example, and you do want to know what is the state from the previous time step and where you want to have that information and use for the next time step data simulation where you do want to use that. And so this gives you a very flexible tool to use that. And also, let's say you run your model and you stop at some point, and later on you want to start from where you stop. And so this initial state file generator module will help you to do that. And so with that, you get a lot of flexibilities in terms of how you want to execute your models. Okay, so those are the 2 points I want to add.
Thank you, Dr. Liang.
Mm-hmm.
I have a question. So regarding the downloading the input data, when you want to like use web services, so you usually like when you request for the data and then you want to download the data for the region, I was wondering if you request for let's say a large region, but you don't have enough memory to kind of load the data at the same time. Does the download module kind of streams the data into disk and then kind of reads it from the disk, or does it like kind of download into memory and then saves it to the disk? So I was wondering how does it work?
So the way CyberWater does this task is it starts downloading one map at a time. It actually moves it to disk first. And in case anything happens, either you disconnect from the internet or the server stop replying, or you lost power or anything bad happened, or you lose memory or you fill up your disk, then CyberWater would stop there. But next time you execute the same workflow, the data sets would pick up from where you left. So you get the same information. You don't have to this doesn't re-download more information that you had to. If there's a memory limitation when you do the execution, I think the problem will let you know, but you will not be able to run this execution. But for this, we do have the capability of doing the execution in HPC, which is what Ranran is going to showcase in the next demo. So we have that possibility in case you don't want to plot the entire data set, or you don't have enough memory to display the entire kind of animation in your computer, and you have that option as well. I hope that answered the question.
Yes, thank you.
Thank you. Thank you for your question.
By the way, I want to jump in. Tony, do we have any poll for this demo?
We do. Thank you for reminding me. Why don't we do this poll right now?
Okay, thanks, Tony.
Okay, it's a very quick one. You should be able to see it now.
Yes, I see it.
Okay, I think everybody that's going to respond Oh, we have a couple more coming in. We'll wait 20 more seconds. Okay.
Daniel, is there a way to reuse the graph or graph both the previous and the current model into same with maybe different colors and things like that to make it easy to compare?
Okay, let me see if I understand the question. So we're displaying two different models, and we want to plot them in this time series that we are showing here.
Daniel, you are not sharing your screen.
This one.
Yes, yeah. So I mean, to compare, for example, the surface runoff from these two models, can they be on the same graph?
Oh yeah. Actually, we can try to do that right now. So you can just copy and paste the model. Just have to remember to change this global file to the previous one, and then okay, we have to connect this main generator. So the main generator goes so the temperature maximum. Yeah, let me just check here. Sorry, just have to double check. Okay, yeah, temperature maximum, then the minimum, then the precipitation, then minimum here, then the precipitation, and then the wind. Precipitation, and then the wind speed. Okay, so we have two equivalent data series, or sorry, generic tools executing the same model. And I have to just plug this, you can just plug this in the same box. It's actually very flexible. Just see what happens. And okay, this guy has a problem. Let me see what's going on. No records. This is, oh, okay. I did not connect the last one. Let me see. 1, 2, 3, and then the wind speed. There you go. Okay. So yeah, you can plot the two different ones in the same one, like this. And you can keep connecting more, and this would plot more. As long as they're consistent, you get a meaningful chart.
Okay, thanks.
Of course. Thank you for your question.
And there is a question in the chat. Oh, okay, I can answer this one. And the question is, how about calibration? Is there a module? That's a good question. Right now, we don't have a module for calibration, but that is one of the things that we plan to do in the future. Thanks. And with that, we will offer people to use calibration algorithm together with their hydroelectric models or other models where they want to calibrate their parameters to get the results that they are in the way they want to have.
Okay. Are there any other questions before we move on? Okay, so Daniel, if you don't mind stopping sharing your screen. The next thing we are going to talk about, or Ran is going to talk about using HPC within CyberWater. It looks like you're sharing your screen, so go ahead and take it away.
Okay, thank you, Tony. Hello, everyone. Thank you for coming.
Excuse me, Ran.
Yeah.
Please use the presentation mode.
Okay, sure. Okay, thank you for coming to today's workshop, and I'm Ran Chen, and I'm going to introduce and give a demo on the high performance computing module in CyberWater. So first of all, in our HPC module, we provide two ways to access the high performance computing resources. The one is wire SSH protocol to connect the HPC platform directly, and the other way is through the gateway. Let me give a brief definition here to explain what is a gateway. A gateway is a mediumware to provide service of executing and moderating distributing application from cluster to computational grids and cloud. And we construct our gateway based on Avarata framework. And I will show you the gateway interface while doing the demo. So far, we have 4 academic HPC platforms, including Bridges 2, Gemstring, Static 2 from Exit, and the Big Red 3 from IU Service. And we have a commercial one, the Google Cloud. To configure the HPC module, user need to provide this information here, like the selection of the platform and the credential for the platform you are going to connect, and the model source used to conduct the computations in HPC platform, and the project configuration information like a project name, the email address, so that you can receive a notification at the beginning and at the end of the job, and the runtime. The runtime is the duration of the text you are going to set, and the argument, the result file prefix. Besides it, the user also need to name the output dataset and give a column index in the result file. This is the similar as the run module agent Daniel has introduced before. Besides that, there are 3 ports we need to connect: the red list from the 3 previous module and the GT path, which brought us the working directory of where the simulation occurs, and the dataset class, the integration of the datasets. That is the HPC interface. User need to drag the HPC module from the modules column, and also do the input port configuration in the input column. And I will give the specific operation in the following demo. This is the workflow I'm going to construct in the demo, with the French Creek dataset and the Wickford computing model. The model in the dashed square is from generic tools. It's just like the Daniel has shown before. The usage of the HPC module is to replace the run model agent, to upload the data and the executable file to HPC platform, and then to retrieve the result from HPC platform. This is an example workflow with our commercial platform, Google Cloud. Just simply click the Google Cloud in this drop list, and then you can connect the Google Cloud with the SSH directly by our module. And while executing the workflow, you can also see some information of the resource and the progress of this job from the black window, the console. And when the job is done, we got a result from the HPC. The result chart is plotted here. Okay, let's start a demo. The previous modules on construction for data preparation, Daniel has already shown before. So let me just drop to the how to use the HPC module in CyberWater Workflow. Go to the agent tool and high performance computing, drag the HPC module here. There are 3 input ports we need to connect. The ready list connect with the 3 previous modules: airwise parameter generator, forcing data file generator, initial state file generator, and the GT path is the working directory, which parsed by the main generator, and this is the dataset class, also parsed from the main generator. For the credential, we need to provide our username. For the HPC platform we wanted to connect, and the file position. I'm going to use 2 datasets here. the surface runoff and the base floor. So we need to name the base floors. Sorry, we need to name the output just like the Daniel did before. Okay, and then choose the model source. You can upload the executable program directly. If you don't have executable program, you can also upload a source code so that high performance computing platform will compile your source code at first and then do the computation. So right now, just upload the executable program directly. You can just click this icon and use the file browser to choose the file you want and then select the platform. First of all, let's start with the SSH platform and the commercial one, Google Cloud, and then configure our project. First of all, give the project a name like CyberWater, and then give your email so that you can have the notification when the job is starting or the ending, the runtime, like give 10 minutes. An argument. Because I'm running the week 4 model, so I need to give a week global global parameter file. So as an argument for the model to run. So that is my argument here. And the result file prefix flags. Okay, that is for the configuration for the HPC module. In order to plot the result, we also need the show chart module here. We are pretty familiar with this module so that we can give it units, like millimeters per day. This one is for the surface runoff. And this one is for the base floor. And the unit is also the millimeters per day. Okay. And you can see there are 2 output for here for the HPC module. Actually, there have a 5 output ports. If you have a more data set need to output, you just click this icon and enable it. Because for this workflow, I only have a 2 data set to output. So, and then connect the output with the MS and show chart. Let me get to feed. That is the configuration for the whole workflow. And then click the execute button to run the floor. And you can see there is a pop-up window showed up and then type in our password. Click OK. And we can see some information from the console, like how many nodes we have for the Google Cloud and how many CPUs, how many memory. For right now, we are just using 1 core in Google Cloud. But in the future, we will provide a user to have a multiple core to use. And we can see how many time we are using for this workflow, like the upload time, the processing time, and download time. Because the data set is pretty small, so the upload time is small. But if the data set is large, the upload time will be a challenging. So what we are working now is just try to downloading the forcing data directly on the HPC platform so that upload time could be safe. That is result get from the HPC platform. And we can see it is the same as the workflow Daniel showed us running on the local machine. Okay, let's move to the bridges, the academic one. I'm trying to use the bridges to share as our academic platform. Click the execute and the password. It is pretty similar as the Google Cloud. The only difference is the resource information. We can see how many CPU, GPU, and other things listed here. And we can see the job ID created. The status called PD, which is short for the pending, and it says we need to wait for 10 seconds. Okay, that is the thing result. Okay, let's move to the platform with the gateway. Because the gateway just provide us a community account so that the user don't need to create or sign in for an individual account. They can also access our gateway. And we have a 3 option here for user to choose in running in the gateway. But we provide a community account, so I'm trying to use the community account here. That's cute. Okay. We can see some programs, and in the black window, like the current state here is showing that our initial state is created. Besides this black window, we also can see our programs in a web browser's interface, like this one. And you can see this job we just submitted a few seconds ago has executing status. We can get a more detail if we click this, like which computer resource we are choosing, or what is your owner, and the runtime we are the runtime, the CPU count, and node count. That is the instance we have created for the community. So the member in our community can use this instance. Issue is due exactly. We need to wait for a while. Because the gateway should do some like a job preparation, and so it might take a little long time than the SSH directory connection. But advantage for the gateway is that you don't need to sign in for your individual's account, and the gateway can help you to manage your project, and you don't need to like connect to the platform separately. You just you use one gateway so that you can connect with multiple platforms. Okay, that is the result shown here. And we can also see the status from this one is completed. Okay, that is the demo for the HPC module. Thank you for your listening.
Thanks, Ran. It looks like, actually, we have one question that came in for, just let me encourage everyone again to type a question if you want, or you can unmute and ask directly. But while you're thinking about that, we have one poll, one more poll. So I'm going to launch that, and everybody, if you could take a second to just complete it. Mhm. We'll give it a few more seconds here. Okay. Thanks everyone for responding to that poll. So our question, which I'm not sure if Yao, if you already answered this in the chat, but the question is, do you need to specify which modules to load onto the HPC?
Yeah, I already answered that. So the module, you don't need to specify, because the module to be loaded to HPC is always your user model module.
Great, thank you. Does anybody else have any questions or comments?
I have a question. I was wondering how the compilation from source works, because it can get complicated. You need to load different modules, compile other libraries that your kind of a program depends on. So I was wondering, how do you kind of pass on this information to the HPC?
We have a two-way to parse the module. Like the first one is we just upload our executable program to the HPC platform directly. Or if you don't have the executable program, you can just provide us your source code folder so that we can have a script to run your source code and compile here in the HPC platform and then run your model. So you need to prepare your model in your local machine, and then we can upload it to the HPC platform.
Sorry, do I interrupt somebody?
Yeah, I wanted to say that my question was about the option where you kind of upload your source code, because for compiling a source code, if you use, like, for example, a CMake, or maybe someone uses Make, and then the CMake itself might depends on another module or another library that needs to be kind of compiled. If there is a dependency, can be complicated. So I was wondering, how does it work?
Yeah, it's a good question. For right now, because we are using the weak agent module, and for right now, we haven't made such complicated situation, but I will consider it because for this right now, we just need a user to provide us the makefile name so that we can run the executable program, which has been generated from the source code. But if it has concerns with other libraries, it might be tricky, challenging for us to sort.
Okay, so let me add on that. So basically, you need to know how do you run your model on the supercomputer. So for example, it need other libraries, other packages. You need to prepare for that. Nobody has that knowledge. So it is the user's responsibility to prepare the other packages, the other modules, the other libraries that you need to use in your compilation to generate your executable. And what the CyberWater does is to upload your entire package, your source code, plus your what other libraries you want to use, and other packages you want to use, upload that to the HPC platform, so that this process, this compile process and the execution process can be remotely carried out.
Yeah, correct. Yeah, if you have other like library need to be compiled with, just upload the other library together with the module you wanted to use in the high performance computing.
So hi, this is Shugong. So I think I just want to ask almost the same question. So about those modules, I think when you want to compile a model on HPC, so it could be complicated because yes, for example, I may need a NetCDF library, but the HPC may already have it, and it is included in certain module. So if you also want to provide your own, for example, NetCDF library and compile it by yourself, there could be kind of some conflicts. So I think because I am a very experienced user of HPC, I think that we have kind of solution. I may make a suggestion. You may consider to use private module. So I mean, if a user provide a specific library and with their model, and you may think about it to just automate some script and create a private module, including all of those dependency. So by doing that, you may, you may like purge all the other modules on HPC and then load your private module. Then you can avoid a lot of conflicts.
Yeah, I agree. Thank you for your suggestion. I appreciate it.
Any other questions or thoughts, suggestions?
So there is a model where, I mean, the user can upload only a part of the code, which can be reintegrated into a bigger framework of this, of the same code. For example, there is a program called NEC 5000 from Oregon National Labs, where you can send some particular subroutine, which you can have your own modifications or your own implementation of a model. But there is already something like a NEC 5000 installed on the supercomputer. But then your modified code, modified subroutine or something can be integrated. And there's already a make file which is optimized for that particular HPC system. And whatever you're sending is not a whole package, but just a particular part of it, and then it is reintegrated and made before you actually use it, in an execution. So that's another way to do that.
Yeah.
So that will reduce. So that requires that some of this higher framework is ready, and the tool to upload a small modified code can be, of course, ingested, which is already there in CyberWater. But then it is integrated and a new executable created on the fly and is used.
So that should be the part of the functionality of the gateway. Is that correct?
Yeah, I know it could be.
Right.
In
Right.
gateway.
Right. I think that gateway can take care of that, right? So that's perhaps the strength of why we need to use gateway.
So gateway has its gateway does help such things, but also it can be done even in the regular SSH access. But then you need to have something to implement this, and then let the users provide the incremental modified module or whatever.
Sure, thanks.
Okay, thanks everyone. Before we end, I'm gonna let Zhu give final remarks, but before we do that, there's one very, very last poll. And the purpose of this poll is to let you know that there is a survey. So I'm going to paste a link in the chat right now to a survey that we would really, really love for everyone to complete. And in the poll, you can, if you really don't want to complete it, that's fine. but maybe you could just tell us if you have copied that. In addition, I will be sending out probably tomorrow a follow-up email, again, thanking you all for joining. This is hugely valuable to our team. So thank you so much for, especially for those of you that were able to stay on for the full 3 hours. In that email, I will have this survey link as well, and also a link to the recording. So if you were unable to stay on for the entire workshop, you can go and watch portions that you may have missed, and then complete that survey. With that, I would like to pass it back to Zhu if you have any concluding remarks you would like to share.
Okay, thank you, Tony. I want to, first of all, thanks to everyone, a huge thanks to everyone for participating in this. And I also want to emphasize the importance of you to help us to get your feedback. So to do that survey that Tony just sent out, the link is very important. And we really appreciate your efforts and your feedback. So please do that. And you know, once you submit your survey, I guess Tony will send you the appreciation, a little gift and the appreciation for your participation and for your completion of the survey. And also, I want to thank everyone from the CyberWater project team and also our 2 students who are who showed you the demos. To hopefully this gives you a little bit of flavor on what CyberWater is all about. And we hope to hear from you on your feedback. And we hope this is a good software system that will help you to improve your efficiency of doing research and education, and spend more time on thinking the core science questions rather than doing the busy headache type of time-consuming and non-vital scientific tasks. So with that, I want to thanks to everyone, and thanks to Tony, Rick, and Zenden and Daniel very much for all your help in making this workshop to be a successful one. And I also want to thank Dr. Yao Liang and Dr. Sudaka for all your feedbacks and helping us answering questions. And of course, I want to thank everyone in the CyberWater project team for all your contributions. Thanks.